All right, thank you for the introduction. I'm Utkarsh. This work has been done in collaboration with Akamai. This work focuses on developing or introducing passive measurement techniques to identify TCP terminating proxies in the cellular networks. So cellular networks comprise of two types of mediums. One of them is wireless and the other is wired. So whenever there is an end-to-end connection between a client and a server, cellular ISPs want to isolate the performance overheads of wireless medium with the wired medium. And so they do it by deploying split TCP proxies. And so CDNs are interested in understanding or detecting whether these proxies exist in cellular ISPs over which clients connect. The reason behind them is CDNs wants to optimize TCP connections by detecting whether there's a proxy or not. They want to know whether they're talking to a client or they're actually talking to a data center that hosts these type of proxies. They also want to monitor web performance with these proxies. Is it good to let the traffic go through a proxy, or should they do something on the application or transport layer so that it doesn't get splitted by the proxy? Active measurement techniques allow detection of these proxies, but these techniques are time consuming. They require access to client devices, and clients are generally care about data. So the question is, given that CDNs do not have access to client devices, can they detect these proxies using HTTP logs or TCP logs, or actually doing something on the JavaScript of the code that the client requests? Is it possible to do it using JavaScript, using passive measurement techniques? So it turns out that yes, it is possible, and in fact, there are three ways you can detect using just the server logs without any client access. And these three techniques are latency-based techniques, packet loss, and some parameters in TCP SYN that the web servers actually receive from either proxy or from the client device. Our data collection methodology to detect these proxies using all these three metrics were based on collecting some data on the client side and collecting some data on the server side. On the client side, we used Akamai's real user monitoring system, which allows Akamai servers to inject some custom JavaScript code that uses navigation timing API and collects time to establish TCP connection, DNS lookup time, and page load times. And then this data is reported back to Akamai by using the same JavaScript. So on the server side, Akamai collects TCP logs, HTTP logs, and so on the server side, we use these logs to find the Akamai's interpretation of packet loss, as well as some parameters in the TCP SYN. For example, initial congestion window size or maximum segment size, as well as the loss related data. So first, we wanted to understand, using the latency-based metric, whether there is a difference between the latency that the clients estimate and the CDN servers estimate. So what we want to measure is these two things. One, the wireless medium, and the other is the wired internet backbone. So we got some data for this. The first two columns here represent the carrier and the country in which the carrier was deployed. The next two columns represent the type of HTTP, application protocol, HTTP and HTTPS. Hits here represent the number of requests that Akamai recorded for each type of protocol and each network. These two columns represent the client RTT column represents the latency estimated by the client using navigation timing API. The server RTT represents the latency estimated by the server. P25, 50, and 75 represents the 25th, 50th, and 75th percentile of the latency distribution. And finally, based on the latency-based technique, in proxy column, we say whether we were able to detect a proxy or not. And in some cases, we say it's limited, and we're going to talk about it more. And in some cases, we cannot predict whether there was a proxy or not using the latency-based technique. So looking at AT&T data for HTTP, we see that there's a huge difference between what servers estimate as latency and what clients estimate. Given that 3 milliseconds of latency on P25 is reasonably low to happen on the wireless link, we say that there is a middle box there to which Akamai servers are talking to. They are not talking to the client because clients experience a latency of 37 milliseconds. We see similar pattern to happen with Verizon Wireless, where P25 of server RTT shows 5 milliseconds of latency, whereas P25 of client RTT shows 36 milliseconds. So there is something in the middle to which these clients and proxies, these web servers are talking to. In Clearwire, for example, we see that latency of server RTT to be very similar to client RTT, indicating that there is an end-to-end connection for all HTTP sessions. So a comparison of client and server RTT can indicate whether there's a proxy deployed by a cellular ISP or not. Next, we wanted to understand whether the latency differences between the end-to-end connection and latency that is only between Akamai servers and these split proxies. So in this example, we compare latency for HTTP sessions and HTTPS sessions only on the server side. So as you can see in this example for AT&T, Akamai servers estimate the latency of about 3 milliseconds for HTTP connections, whereas for HTTPS connections, they estimate a latency of 52 milliseconds. Now there has to be something in between that's generating HTTP traffic, and that is not the client, because if that was a client, we would see much higher latency than 3 milliseconds. So using only the server-side logs and by comparing HTTP and HTTPS sessions latency, we can detect whether there's a proxy or not. But there's something interesting in this data. Look at the T-Mobile data. The server RTT of P25 shows 19 milliseconds, whereas P50 is 68. 19 is still reasonably low to be true on the end-to-end connection that comprises of wireless and wired. However, P50 seems reasonable to be on a cellular network. So let's look into what's happening in T-Mobile's network. To understand what's going on in T-Mobile network, we classified our data based on the domain name as well as the location where Akamai servers were there. So we found in this data that for a clothing website, and it could be any website, clothing website in California, servers estimate a latency of only about 2 or 3 milliseconds, whereas the clients estimate a latency of about 37 to 40 milliseconds. Other website in California did not, for any other website in California, Akamai did not observe any connections to be split. So this shows that T-Mobile specifically, and there might be other networks as well, they deploy proxies that are based on domain names. They split connections based on the domain names. The same clothing website, which is here, in Texas does not go through a proxy. That means these proxies are also configured to split connections based on the locations from where the requests are coming. Next, we wanted to understand whether these proxies exist in IPv6 infrastructure deployed by different ISPs. At the time of this study was conducted, we were only able to see high traffic from these 3 major cellular carriers in the US. In IPv4, in the data where we showed IPv4 data, we found that Verizon Wireless has a proxy that splits IPv4 HTTP connections. Whereas in case of IPv6, they do not have a proxy because server-side latency is very similar to client-side latency. So latency-based techniques could be used to monitor how and when and in which scenarios a proxy is being used by different cellular carriers. The last thing we identified using the the latency-based technique was that in a cellular network in France Telecom, they split HTTPS connections. We do that, we identify that because the server-side latency is extremely low, and it matches the HTTP latency. So this indicates that France Telecom is splitting both HTTP and HTTPS connections. So we could use a latency-based technique to monitor whether our secure content is being split or not. Next, we wanted to find a second way of just confirming whether our latency-based techniques are accurate in detecting these middle boxes. So we use packet loss as the second metric to just support our results. So in this graph, we try to plot the interpretation of packet loss on the server side for both HTTP and HTTPS connections. The x-axis shows the percentage of packet loss. The y-axis shows the CDF of TCP connections that we were able to collect data for. In this, there is a general trend that for HTTP connections, we see very low packet loss. For example, almost about 100% of the connections on AT&T, which is the solid dot, there were no packet loss because AT&T has a proxy for splitting HTTP traffic, and because the communication is happening between two giant data centers, it may be expected to observe that there won't be a packet loss, or at least Akamai would interpret it as a packet loss. However, for the hollow symbols like triangles, circles, and squares, we see that since we see a high packet loss, that also indicates that Akamai servers are not talking to proxies, and instead there is an end-to-end connection between the servers and the clients. We wanted to confirm whether France Telecom was actually splitting connections on HTTPS traffic or not. So we collected data for data that shows packet loss on France Telecom for both HTTP and HTTPS traffic. We see here that for both type of traffic, there is almost no packet loss that Akamai actually interpreted. So this also indicates that the end-to-end connection is not there between client and CDN servers, and instead it's between the TCP terminating proxies and CDN servers. Last, we wanted to find the third parameter that we could actually support the conclusions from the other two metrics, and we used some parameters in the TCP SYN packet that gets received by CDN servers. One of the parameters was to look at the initial congestion window size in the SYN packet. The other was the maximum segment size, and the third was the TCP timestamp value in the TCP options header. What we found was that for all SYN packets for port 80 for HTTP traffic, they had the first two values exactly same, but the third value was incremental. That indicates that all SYN packets were coming from one single machine, and because the TCP timestamp values were incremental by a value of less than 10 around, it indicates that there is one single machine that's generating all those SYN packets, and it's not the client. Because we ran some side active experiments, and we identified that different mobile devices actually have different congestion windows and maximum segment size, and they also have different timestamp values. So if Akamai is receiving the same all three values to be same, then it has to be coming from one single machine. For HTTPS traffic, for all the TCP SYN packets for HTTPS, we found that these values were different, indicating that they are actually being generated by different mobile devices, client devices, and not just one machine. So we know we have different techniques to detect these proxies, but what about accuracy? There have been previous studies that talk about running active experiments and detecting these proxies. So we wanted to compare the level of accuracy that our passive measurement techniques can offer in comparison to the active measurement technique from Zhu et al. In last year's PAM. So we compared the delayed handshake metric that this study used as a representative of detecting TCP terminating proxies, and we found that for all major US carriers, all three of our techniques were able to identify that there was a proxy similar to what this active measurement technique did. So some takeaways from this study is that we can still use passive measurement techniques on the server side, and not only CDNs, but any server operator could use one or more of these techniques to detect the presence of these proxies from their logs. They don't need client access. So instead of running active experiments, we can just do it from passive measurement techniques. The other thing is passive measurement techniques are mostly accurate. In some cases, it might be difficult to detect whether it's a proxy or not, and in those cases, active experiments may be useful, but in majority of the cases, we can detect proxies with passive measurements. And finally, our work offers a peek into how a large CDN collects performance data related to their customer websites. And so if you're interested in understanding how Akamai collects performance data and how they run analysis of this data, you can go ahead and find more details in the paper. With that, I thank you, all of you, and I'll take questions if there are any.
So there's time for a few questions.
So are you saying that France Telecom is actually, are you saying that the France Telecom is actually, they are man-in-the-middle attack?
I don't say whether there's a man-in-the-middle attack. They are just splitting proxies. I don't know if it's violating user privacy or not, because it would be only violated if the proxy presents a bogus certificate to the user. But we don't know. The goal of this was to just understand whether there's a way we can detect these proxies and not exactly how they function. So, yeah.
Okay. Second question was, how does Akamai know from server logs which server providers data coming from? Sorry, for TCP especially, for TCP characteristics.
So we have this tool. So Akamai has this tool called Akamai Escape, which does DNS name lookups, reverse name lookups on the hops on the trace routes, which also does trace routes, of course. It gets some information from ISPs, and what we did was we passively collected some TCP SYNs from running Wireshark on multiple servers, and we actually feed those IP addresses into Akamai Escape tool and found out whether the IP was actually a cellular or not cellular and which ISP it belonged to.
So given that you actually know the deployment of Akamai clusters, why didn't you use that to validate basically the latencies rather than just use the numerical relative latencies, which are no ground truth? Because in the case that they are too similar, that doesn't prove that there are no middleboxes. So
right. In some cases, it could be that Akamai is talking to a proxy that is very far in the network, right? But in those cases, we would see we would see that client-side latency is also very high, and Akamai, the latency estimated by Akamai is also very high. And in such cases, we say that it may not be ideal to use latency-based technique, but you can use some other techniques which are packet loss-based or looking at parameters in TCP SYN to find whether there's a proxy or not. And even then, if these three techniques are not reliable, then we suggest the use of active experiments.
okay, another question, why didn't you use tracebox as well as another technique to check middleboxes? That would be the closer to the ground truth.
I don't remember Tracebox right now, but I believe they use active experiments. I may be wrong, but we can talk more. What's that?
You can talk to them just in front of them. They're here.
Okay. Yeah, we can talk offline about it, but I believe I've read that paper. I do not remember right now, but yeah. I should be. I'll get back to you after I talk to him.
Maybe a last question before the lunch break. Okay, well, now maybe very helpful there. So thank you very much for your attention and the nice question and discussion. And thank you very much to all the speakers.